In this video, we are going to talk about polynomial functions. This is AP Precalculus topic 1.4. This is the formal definition of a polynomial, so you can just go ahead and soak that in for 1.5 seconds. A polynomial is a sequence of terms like this, where these red numbers, a0, a1, a2, a3, all the way up to an, are called the coefficients. And these can be any real number. These coefficients are paired with a variable and an exponent, like x to the third power, x to the second power, x to the first power, which I didn't need to write, and even x to the 0 power, which pairs up with a 0. X to the 0 power is just a 1, and so we don't really need to write that. So here's an example of a polynomial. The coefficients are the 3, the -1, the 5, the 7, and the -2. We would not really write the 1. It would be understood. This polynomial has 5 terms. 1, 2, 3, 4, 5. The exponent of each term is called the degree of that term. So the first term has degree 4, the second term of this polynomial has degree 3, and so on. The last term, where I have written in the x to the 0 power, but I could erase it again without changing the polynomial, but we would understand that this constant term has degree 0, because it's like 3 times x to the 0 power. The leading term is the term that has the highest degree. So -2x to the 4th power is the leading term of this polynomial. When we write the terms in order of degree from highest to lowest, it's called standard form. But if we rearrange the polynomial, this term would still be the leading term because it still has the highest degree. So watch out, the leading term is not always in the front. The coefficient of the leading term is called the leading coefficient of the polynomial. So the leading coefficient of this polynomial is -2. The degree of the leading term is considered the degree of the whole polynomial. So we would say that this polynomial has degree 4. The highest exponent in the polynomial, that's the degree. Keep your eye on this term right here because it's about to disappear. This is now a polynomial that has 4 terms, but it is still a polynomial. It's okay that it goes straight from degree 1 to degree 3. Every degree doesn't have to be there for it to be a polynomial. For the model polynomial they gave us in the definition, the leading term would be the an x to the n power. The degree of the polynomial is the exponent of the leading term, so the degree would be whatever n is, and the leading coefficient is this number in front, which is an. For polynomial f of x, the leading coefficient is the 3, and the degree is the 4. For polynomial y, be careful, the leading term is this one because that's the one that has the highest exponent. So the leading coefficient is -7, and the degree of the polynomial is 3. The leading coefficient of g of x is the only coefficient. This constant on the end is the only coefficient, so it must be the leading coefficient. Now as far as the degree, a constant will always have degree of 0, and that's because we can think of this polynomial as 4x to the 0 power. X to the 0 power is just 1, and 4 times 1 is just 4. So nobody needs to write that stuff. Now let's talk about extrema. The extrema of a graph are the minimums and maximums of a function, or we really should say the minima and maxima of a function. The plural of minimum is minima. There are 2 types of extrema. There are relative extrema versus absolute extrema. Relative extrema are also called local extrema, and absolute extrema are also called global extrema. A polynomial has a relative min or a relative max wherever it switches from decreasing to increasing, or vice versa. If it switches from increasing to decreasing, you're going to have a relative max. Or you could have a relative min at an endpoint for a function that has a limited domain like this one. So where are the local minima of this graph? Look for the bottom of a dip, and you are looking at a local minimum. So there's one here at x equals 0. But we should also include the bottom of this end of the graph. Since it does have a limited domain, that endpoint at the bottom is a local min. That's at x equals -4. For local maxima, look for the top of hills or peaks. So we see that we have a local maximum here at x equals -2, and we have another one here at x equals 3. Now let's talk about absolute extrema or global extrema. For example, the absolute maximum of this graph is the highest point on the graph. If you are asked what is the absolute maximum, you are being asked for a y value. So we would say that this function has an absolute maximum of 2. If you mention the x value, that's telling you where the absolute maximum occurs. So this absolute maximum is at an x value of 3. So putting it all together, this function has an absolute max of 2 at x equals 3. What about absolute minimum? That's going to be the lowest value on the entire graph. At first glance, it looks like this point right here is going to be the absolute minimum. But if you look closely, I see an arrow right here. So this graph looks a little bit misleading. You have to understand that this graph with the arrow means that it's unlimited. So this will continue on forever down. So this graph actually has no absolute minimum. So I'm not sure if that's what the author of this problem intended. So just for fun, I think I'm going to make a little modification here. If we limit the domain on the right-hand side like this, then this point on the left does become the absolute minimum. And we would say that this function has an absolute minimum of -3, you say the y value, at an x value of -4. I just checked the answer key, and this problem was intended to be a little bit tricky. With the arrow, there is no absolute minimum. Example 2. Does this simple function have a relative minimum anywhere? It does not. We don't see the bottom of a little valley or something, and there is no endpoint that we can use as a relative minimum. So we're going to say NA, or we could just say none. Does this curve have a relative maximum? Yes, at the top of a hill like this will be a relative maximum. So we have a relative max at x equals 1. What about an absolute minimum? Well, if there is no relative minimum, there cannot be an absolute minimum either. So we're going to say none again. What about an absolute maximum? Well, here's where we find out that a relative maximum can also be the absolute maximum. And that's the case here. We only have the one relative maximum, and it is also the highest point on the graph. So we have an absolute maximum that is equal to 3. So we have an absolute max of 3 at x equals 1. All right, how about part B? Relative minimum. So I see that we have a relative min right here. So that's at x equals -2. Let's talk relative maxima. So obviously at the top of this hill, that's going to be 1. So we have a relative max at x equals 3. There is another one. Because of the limited domain, the top end of this left side of the graph is also a relative max. So I feel like I should put a comma and put x equals -4, because that's another location of a relative max. How about absolute min? So this is our relative min. Is this also the absolute min? Well, no, we're not going to fall for this again. We see the arrow over here, which means that this really goes down forever. So this is not the lowest point on the graph. There is no lowest point on the graph. It just keeps going down, down, down. So for absolute min, we're going to say none. For absolute max, this relative max is also the absolute max. So we're going to say we have an absolute max of, and you say the y value now, so absolute max is 2 at x equals 3. Move your eyes over to part C, looking for relative minima. So definitely we will look at the bottom of any dips. So we have a relative min at x equals -3, and we have another one at x equals +3. These endpoints are high points, so we'll save those for relative maxima. In fact, let's get to that right now. So relative maxima at the top of this hill, that's definitely going to be one. But also these upper ends of the endpoints here, these endpoints, because of the limited domain, and they're at the top of the ends. So these are also locations of relative maxima. So we have 3 of these. We have one at -4, and we have another relative max at 0, x equals 0, and we have another one at x equals 5. How about the absolute minimum? This graph has one. It's obviously going to be one of these two. The lowest absolute minimum, well, the lowest relative minimum is here. So we have an absolute minimum of y value. So absolute minimum equals -3 at x equals, and by coincidence that happens to also be -3. Does this graph have an absolute maximum? It does. These are not arrows. So there is an absolute max, and the highest point on the graph is here. So we have an absolute max of 4 at x equals 5. When we talk about the zeros of a polynomial, we are talking about the x-coordinates of the x-intercept. So between two real zeros of a polynomial, there must be at least one relative max or relative min. That makes sense, because if we have two x-intercepts and a polynomial is always going to be continuous, it's either going to go up and then it has to come back down. So there's going to be a relative max in there somewhere. Or maybe it went down and then came back up. So then there would be a relative min in there somewhere. You could have more than one, right? If we have, if these are both real zeros, there's nothing to say that the polynomial doesn't do like this. So there could be two relative, well, there are three relative extrema the way I have it drawn. There are two relative maxima and one relative minimum, but there's at least one. For a polynomial with even degree, the end behavior on both sides is always the same. So, for example, here's a polynomial of degree 2. Notice it rises on the left and the right. Here's another even degree polynomial, degree 4. This one rises on the left and rises on the right. The only other option is to be falling on the left and the right. Because of that, we can say that polynomials of even degree must either have an absolute max or an absolute min. Don't forget that a relative max or min can also be called a local max or min, and that an absolute max or min is sometimes called a global max or a global min. Let's talk concavity for a minute. We know that any part of a bowl shape like this is considered concave up. It does not have to make a complete bowl. This blue function is concave up as well as the red function. Similarly, all three of these functions are concave down. A point of inflection occurs when a function changes from concave up to concave down, or from concave down to concave up. So for example, looking at this graph, we can see that it is concave up in this area, and then it is concave down in this area. So somewhere in between there must be a point of inflection. Also note that at a point of inflection, the rate of change of a function changes from increasing to decreasing, or from decreasing to increasing. I encourage you to memorize this chart showing the graphical relationships between f, the rate of change, and the rate of change of the rate of change. And if you have memorized that, then you know that if f is concave up, then the rate of change is increasing. If f is concave down, that means the rate of change will be decreasing. So of course, if we say that a point of inflection is where f changes from concave up to concave down or vice versa, then a point of inflection will also be where the rate of change switches from increasing to decreasing, or vice versa. We could even talk about the rate of change of the rate of change. We could say that a point of inflection will occur where the rate of change of the rate of change changes signs. Example 3a. Find any values of x where g has a point of inflection. So as I mentioned a moment ago, we can tell that the graph is concave up in this first part, and then at some point it switches to being concave down. So we have to estimate a little bit, but it seems like we have a point of inflection right here at x equals -1. All right, it would be reasonable to say that we're going from concave up to concave down right here. But then it switches again at some point, and again I'm going to estimate and say that it switches from concave down back to concave up right about x equals 1. For each of the following intervals, determine if the rate of change of g is increasing or decreasing. Explain your reasoning for each answer using features of the graph of g of x. So let's examine the interval from 3 to 4. That's this part of the graph right here. We can use concavity to answer each of these questions, and the interval from 3 to 4 is sitting on part of the graph that is clearly concave up. And again, when f is concave up, the rate of change is increasing. We can say the rate of change is increasing because g of x is concave up, and these abbreviations are accepted by the College Board. The interval from -4 to -3. That is another portion of the graph that is concave up. The rate of change is increasing because g of x is concave up on the interval from -4 to -3. We should include this interval in the answer, so I've retroactively gone back and included the interval in the previous answer as well. Do that going forward. On the interval from -1 to +1, g of x is concave down, so we know the rate of change will be decreasing. We'll say the rate of change is decreasing because g of x is concave down on the interval from -1 to 1. How about the interval from 1 to 2? Well, from 1 to 2 is this portion of the graph right here. which is again a part of the graph that is concave up. So that means the rate of change will be increasing. We'll say the rate of change is increasing because g of x is concave up on the interval from 1 to 2. Let's finish off this video with a calculator problem. So go ahead and take out your TI-84. Go ahead and hit your y equals button, and I see that we're given this function here. I haven't really read it yet, but I can bet that we need to type this function in as y1 on our calculator. So go ahead and do that right now. Make sure you used this white negative sign in parentheses for the negative leading coefficient. So let's get back to reading the problem. On the interval, the closed interval, from 0 to 3, the number of cars in a parking lot at time t hours can be modeled by this function. Based on this model, at what time t does the number of cars in the parking lot change from increasing to decreasing? Seems like we are about to estimate by looking at the graph. But first we need to adjust the window. So head over to the calculator and hit the window button. For starters, we can't have negative cars, and we don't have negative time. So we know that x min and y min can both be 0. Also, for the x interval, for x min to x max, they gave us the interval from 0 to 3. So that means we should definitely go ahead and set x max to be 3. As far as the y max, we don't know how many cars we're going to be dealing with. I think I'm going to put 10. I very often will just put 10 as a starting point. We can always adjust this later. So let's hit graph and see what we've got. Okay, so I can see that the number of cars went significantly higher than 10. So let's go back to the window and let's change that y max. I think I'm going to just jump all the way up to 30. And hit graph again. Okay, almost. I think I'm going to go all the way to 50. Just I'm through playing around. Okay, so the question is asking, at what time t does the number of cars change from increasing to decreasing? So they're describing the location of the relative max, or even the absolute maximum in this case. So how do I find the absolute maximum or a relative maximum using my calculator? Hit second trace, and it won't surprise you that we will use the function called maximum. So you can just hit number 4. Where it says left bound, make sure your pointer is really anywhere here to the left of where the relative maximum is. So where it is right now is fine. I'm going to move a little bit closer. So hit enter. Now it's going to ask you for the right bound. You want to move the pointer somewhere that is clearly to the right of the relative max. So I'm going to use my right arrow key and move to the right of this relative max and hit enter. Then it's going to ask you for a guess. I encourage you to move the pointer as close as possible to about where you think the relative max is. It just helps the calculator think faster. And hit enter. So the number of cars changes from increasing to decreasing at time t equals 2.446. Let's not forget the units, very important. So at t equals 2.446 hours, or the College Board will accept t equals 2.445 hours. They don't care if you round or truncate. as long as it's accurate to the third decimal place. Hey guys, don't forget to like and subscribe, but also if you found this video helpful, there's a lot more where that came from. You can click the upper link, which will take you to the whole unit playlist, or you can click the lower link, which will take you to the next video in the playlist. See you there.